Welcome back to my class in number theory. For today, we will continue our discussion of the floor or the greatest integer function. And we will define the decimal representation of a positive integer. But before we get to the definition of the decimal representation of positive integer, we discuss first some alternative definitions of the greatest integer function or the floor of a real number. We let x be any real number. In particular, we let x be equal to 2.3. Then we find the floor of 2.3 or the greatest integer function x when x is 2.3. The greatest integer of x is defined as the smallest integer that is less than or equal to x. For the particular value of x equals 2.3, the greatest integer function of 2.3 or the floor of 2.3 is the largest integer that is less than or equal to 2.3. Again, for any real number x, the floor or the greatest integer function x gives the greatest integer that is less than or equal to x. For the particular value of x equals 2.3, the greatest integer function of 2.3 or the floor of 2.3 is the largest integer that is less than or equal to 2.3. And that integer is 2. Now suppose we write all the integers that are less than or equal to 2.3. We take the set of all integers that are less than or equal to 2.3. The set of all integers denoted by n. N is an integer, so n is an element of set Z, the set of integers that includes the negative integers, the zero integer, and the positive integers. We write all the integers such that the integer n is less than equal to x. X is in particular equal to 2.3. And that set is the set containing these integers 2, 1, 0, negative 1, negative 2, up to negative infinity. All these integers, all these numbers are elements of the set of integers C. And all of these numbers or integers are less than 2.3. N is less than or equal to 2.3. But for this particular example, all these integers are strictly less than 2.3. But nevertheless, this inequality sign is satisfied by all these elements of this set. Now, if we take the maximum element of this set, if we take the largest element of this set, the largest element of this set is 2. We write the maximum of this set containing the elements 2, 1, 0, negative 1, negative 2 up to negative infinity is 2. The largest element of this set or the maximum of this set is 2. But we find that 2 is the floor or the greatest integer function of x if x is 2.3. Hence 2, which is the maximum of this set, is equal to the maximum of this set, which is equal to 2, is equal to the floor of 2.3 or the greatest integer function of x when x is 2.3. And now we generalize this result to write an alternative definition of the greatest integer function x, where x is any real number. This is the alternative definition for the greatest integer function x, where x is any real number. For any real number x, the greatest integer function of x is equal to the maximum, the largest element of this set consisting of integers and element of c, such that the integers n are less than or equal to x. The elements of this set are all real numbers, are all integers that are less than equal to the given real number x. And the largest element or the maximum of this set is defined as the floor of x or the greatest integer function of x, where x is a real number. And this is a particular example when x is 2.3. We enumerate all the integers that are less than or equal to 2.3. So we have the integers 2, 1, 0, negative 1, negative 2, up to negative infinity. And when we take the maximum of this set, the largest element of this set, which is 2, we get actually the floor of 2.3 or the greatest integer function of x when x is 2.3. We state another alternative definition for the floor of a real number x. We consider again the greatest integer function of x for x equals 2.3. Suppose we are given the greatest integer function of x where x is 2.3, then we have shown earlier that the floor of 2.3 or the greatest integer function of x when x is 2.3 is 2. And we let 2 be equal to n. Then, from this equation, it is clear that 2.3 is greater than 2. 2.3 is greater than 2, but 2.3 is less than 2 plus 1. 2 plus 1 is 3 and 3 is greater than 2.3, but 2.3 is greater than 2. And we generalize this result. In general, in general, for any real number x, and the greatest integer function of x is n, that is the floor of x, any real number, we say that x is greater than n, but x is less than n plus 1. And this is a particular example when x is 2.3. The greatest integer function of x is 2, that is your n. And we obtain this relation, the x 2.3 is greater than its floor 2, which is n, but less than its floor 2 plus 1. So in general, for any real number x such that the floor of x is equal to n, then x is greater than n but less than n plus 1. Now suppose that the real number x is an integer, say 2. Suppose x is an integer, 2 is an integer, but it is still a real number. Then the floor of 2, or the greatest integer function of x when x is 2, is equal to 2. And we take 2 as n. And you can see that this x2 is exactly equal to n, which is 2. But the x is 2, is strictly less than 2 plus 1, where 2 is n, the floor of 2. We generalize this result. In general, for any integer x element of C, such that the floor of x is equal to n, actually this n here is exactly equal to x, because x is an integer and the floor of an integer is equal to itself. So we write x is equal to n, but x, the integer n, is less than equal to itself plus 1. Now we combine this result and this result into one statement, and we write now the second alternative definition of the greatest integer function. We now combine these two results and we write more generally for any real number x. We say that the greatest integer function of x for x is any real number is equal to n if and only if we have these two conditions. So we write if and only if x is less than n, x is greater than n, or x equals n. We combine these two, x greater than n and x equals n into 1, and we write x greater than equal to n. Greater than, x is greater than or equal to n. But x in both of these statements, x is strictly less than n plus 1. X is strictly less than n plus 1. And we have the second alternative definition of the greatest integer function, or the floor of x, where x is any real number. For any real number x, the greatest integer function of x is equal to n if and only if x is greater than or equal to n, but x is strictly less than n plus 1. And these are the two particular examples. If the real number x is not an integer, say 2.3, the floor of 2.3 is 2, and you can see that 2.3 is greater than its floor 2, but less than its floor plus 1. If the real number is an integer, say 2, its floor is equal to itself, and this integer 2 is equal to its floor, which is itself, but the integer 2 is strictly less than to its floor or itself plus 1. And we combine these two into one statement to arrive at the second alternative definition of the greatest integer function. The second alternative definition of the greatest integer function, we derive another important relation. We say that for any real number x, element of R, for any real number x, element of R, if the greatest integer function of this real number x is equal to n, then focus your attention to this inequality. This relation is satisfied. X is greater than, equal to n, or n is less than or equal to x. N is less than or equal to x. If x is any real number and the floor of x is equal to n, then from the second alternative definition of a greatest integer function, n is less than equal to x. But n here is equal to the greatest integer function of x, or the floor of x. Hence, this relation implies that n, replace now n with the greatest integer function x. Thus, the greatest integer function x we have shown is less than equal to x. An example is 2.3. If the real number x is 2.3, we check if this relation or inequality is correct. This inequality says the floor of x, that is the floor of 2.3, should be less than equal to x. And for this particular value of x equals 2.3, we have the greatest integer function of 2.3. Should be less than or equal to 2.3. But by definition of greatest integer function, the floor of 2.3 is the greatest integer that is less than or equal to 2.3, and that integer is 2. And 2 is strictly less than 2.3. This inequality is still satisfied. If the real number x is an integer, say 2, then the floor of 2 will be exactly equal to 2. And we state that as a note, number 5. If x is 2, then we check this relation. The floor of x is less than equal to x, where x is 2. We replace x with 2. But the floor of 2 is equal to itself. The greatest integer that is less than or equal to 2 is 2. And 2 is equal to 2. Thus, this relation is still true for x if x is an integer, say 2. And we generalize this result in number 5. In number 5, we now write the floor or the greatest integer function x is equal to x if and only if x is an integer. And the example, and this the particular example we had, if x is 2, 2 is an integer, the floor of 2 is 2 and it's equal to itself, 2, which is our x. In general, if the floor of x is equal to x, and then it means that x must be an integer. That is, this will only be true that the floor of x is equal to x if and only if x is an integer. We now take an example to make use of the alternative definitions of greatest integer function to prove a theorem. We now take one example to use the alternative definition of greatest integer function, and this example is actually a theorem. Prove that for all real numbers x, then the greatest integer function of x is less than or equal to x, but is strictly greater than x minus 1. It will take 3 steps to prove this theorem, and we will use one of the alternative definitions of the greatest integer function. And we start with the given. We are given that x is any real number. So we let x be any real number such that the floor of x is equal to n. The value of the greatest integer function is always an integer. So if n is an integer, it is an element of the set Z of integers. The value of the greatest integer function is always an integer. That is why it's called greatest integer function. The greatest integer function of x is the greatest integer that is less than or equal to x. Now it is to this equation, the greatest integer function of x equals n, that we will apply the alternative definition of greatest integer function. The alternative definition of greatest integer function says that the greatest integer function is equal to n if and only if x is greater than or equal to n but strictly less than n plus 1. And we start from this part of this inequality. If n is less than or equal to x, then we can replace n with n is equal to the greatest integer function of x. If n is less than or equal to x, then the greatest integer function of x is less than or equal to x. And so we already obtained the second part of this inequality. The greatest integer function of x is less than or equal to x. And we obtained the first part of this inequality by using this second part of this inequality. We write also if x is strictly less than equal to n plus 1, x is strictly less than n plus 1, we transpose 1 to the left-hand side of this inequality, or we subtract 1 from both sides of this inequality, and we will get x minus 1 is strictly less than n. From this inequality, we subtract 1 from the right side, we subtract 1 from the left side, and we get x minus 1 is strictly less than n. But n is the floor of the greatest integer function x. Thus, from this inequality, we conclude that x minus 1 is strictly less than the greatest integer function x. We now combine the two results, this part and the result from the second part of the proof, and we make the conclusion in the third part of the proof. We now conclude that the greatest integer function of x is less than equal to x, as we have shown in the first part of the proof. And the greatest integer function of x in the second part of the proof, we have shown is strictly greater than x minus 1. The greatest integer function of x is less than or equal to x, and the greatest integer function of x is greater than x minus 1. The greatest integer function of x is strictly greater than x minus 1. And this completes the proof of this theorem that says for any real number x, the floor of x is less than or equal to x, but strictly greater than x minus 1. Now we will state the definition of the decimal representation of a positive integer. We now define the decimal representation of a positive integer. We consider the exponential number 3 to the power 12. And we denote this number by, this is a number in exponential form. We denote this number by small letter a. Using your calculator, you can compute 3 to the power 12, and it should be equal to 531,441. This 531,441 is called the decimal representation of this number in exponential form 3 to the power 12. And you can see that it's not really a decimal number because there is no decimal point and no digits after the decimal point. It's actually a whole number, a positive integer. And later on you will see why this is called a decimal representation of this positive integer in exponential form 3 to the power 12. But for now, this is the decimal representation of this number in exponential form 3 to the power 12. And you can see that in this number, there are how many digits? 1, 2, 3, 4, 5, 6. There are 6 digits in this number. So we say the positive integer 3 to the power 12 is a 6 digits number. Again, we say that this decimal representation of this number 3 to the power 12 is a 6 digits number, because in the decimal representation of this number in exponential form 3 to the 12, there are 6 digits in this decimal representation of this number 3 to the power 12. And we let this 6 be equal to n. Now this number a, 531,441, can be written as follows. The first digit is 5. And multiply that by 10 to the power 6 minus 1, 5. If you will multiply 5 by 10 to the power 5, you will get 500,000. And to 500,000, we will add 30,000. The second digit now is 3. To this number, we add plus 3. Multiply by 10 to the power 4. From 5, the exponent of 10 will be decreasing from 5. And the exponent of 10 begins from n minus minus 1. In our example, 6 minus 1, 5. The next digit in this number is 3 multiplied by 10 to the power 4. The next digit is 1, and to the sum of these two numbers we add 1 multiplied by 10 to the power 3. The exponents of 10 are decreasing by 1. 5, 4, for the next term, the exponent of 10 will be 3. And the digit after 3 is 1 multiplied by 10 to the power 3. The next digit is 4, and we multiply 4 by 10 to the power 2. 10 to the power 2 is actually 100 multiplied by 4, and you will get 400. The next digit is 4, and we multiply that by 10 raised to 1. And the last digit is 1. And we multiply 1 by 10 to the power 0. But 10 to the power 0 is equal to 1. So we can simply write 5 times 10 to the power 5 plus 3 times 10 to the power 4 and the last term is 1 because 10 to the power 0 is 1 multiplied by 1 is 1. Now this is a real number, and the reason why this is called a decimal representation of this number is that when you write this number in this form, the digits of this number, each digit of this number is multiplied by a number with a base of 10. And you recall that in the decimal system, the numbers are expressed with a base of 10. And that is the reason why this 531 for 441 is called a decimal representation, because it can be expressed or it can be written as a sum of the product of the digits of this number and a power of 10. A number with powers of 10 with a base of 10 raised to some exponent. Now we generalize this statement with a particular example. Suppose now A is any real number, and we write that number in this form. You can also see that in this expansion of this positive integer 531,441, there are 6 terms in the sum. 1, 2, 3, 4, 5, 6. And so this number, positive integer, which is called a decimal representation of the positive integer in this exponential form, is a 6 digits number. If you write this using base 10, there are 6 terms in the sum. Now we generalize, writing a real number A as a sum of its digits multiplied by powers of 10. In general, we take any real number, any positive integer a. The positive integer a is an n digits number, which means that the decimal representation of this positive integer has n digits. And suppose this positive integer a has this decimal representation. The digits of a are a sub n minus 1. In our example, that is 5. A sub n minus 2 in our example is 3. A sub n minus 3, that is 1. And the last digit in this decimal representation of the positive integer a sub 0 is 1. And we will now write this positive integer a as a sum of the digits multiplied by powers of 10. A now in this form is equal to the first digit of a sub n minus 1, multiplied by 10, the first exponent of 10 is n minus 1. And n is the number of digits in a. And we are given that a, the positive integer a, is an n digits number. Hence, the first exponent of a is n minus 1, which is the subscript of the first digit a sub n minus 1. The next term is the second digit a sub n minus 2. As I said earlier, the exponent of 10 is decreasing. So next to n minus 1 is n minus 1 minus 1 or n minus 2, which is the subscript of the second digit of a. The next term is the third digit a sub n minus 3. Multiply by 10 to the power n minus 3. Plus, up to plus, the third term from the last is a sub 2 multiplied by 10 is squared. The second to the last term is the digit a1 multiplied by 10 raised to 1. And the last digit is the last term in the sum is a sub 0. So we have written the positive integer a as a sum of the products of its digits, the digits in its decimal representation, and the powers of 10. Where a here is a positive integer with n digits. A is an n digits real number. Now in some cases we cannot expand, we cannot actually write the number in exponential form as a positive integer because there is a limitation in the number of digits that can be displayed in the calculator. But we can tell how many digits are there in the decimal representation of a number in exponential form. If we are only interested in the number of digits in this positive integer 3 to the 12, we do not have to write the decimal representation of 3 to the power 12 in this form and count the number of digits. And that is our next topic in our example. We now write a method for finding the number of digits in a positive integer. And this method will make use of the greatest integer function. This is actually an application of the greatest integer function in finding the number of digits in the decimal representation of a positive integer. If a is a positive integer, then the number of digits denoted by small n in its decimal representation is given by the greatest integer function of the logarithm of a plus 1. Plus 1 here is a constant, it's always plus 1. And so the greatest integer function, or the floor of the logarithm of a, which is the positive integer given, plus 1, is equal to n, the number of digits in the decimal representation of the positive integer a. We take an example. Find n, the number of digits in the decimal representation of each positive integer. We had this example earlier. We have the positive integer in exponential form 3 to the power 12, and this is our a. And we want to find the number of digits in the decimal representation of the positive integer 3 to the power 12. And using our calculator, we computed that 3 raised to 12 is actually 531,441. And counting the number of digits in this positive integer, this is the decimal representation of a of the positive integer 3 to the power 12. We say that there are 6 digits, 1, 2, 3, 4, 5, 6, 6 digits in the decimal representation of 3 to the power 12. Now we will check if this 6 is correct using this method. The number of digits in the decimal representation of 3 to the power 12 is equal to the logarithm of a, the floor of the logarithm of a plus 1. And a is in exponential form 3 to the power 12. Plus 1. And to the logarithm of 3 to the power 12, we apply a property of logarithm. You can see that the base is not indicated. If the base is not indicated, that means that this logarithm is a common logarithm, which means that the base is 10. A common logarithm is a logarithm to the base 10. But if the base is not indicated, it automatically means that the base of the logarithm is 10. And this is the one that you have in your calculator. In your calculator, there is a key that says log, and it means a logarithm to the base 10. If the base of the logarithm is e, then it is called natural logarithm. And by property of logarithm, is one of the properties of logarithm. The logarithm of x to the power n is equal to n times the logarithm of x. And applying this property of logarithm, this is now equal, the logarithm of 3 to the power 12 is equal to 12 times the logarithm of 3. Again, by property of logarithm, the floor of the logarithm of 3 to the power 12 is equal to 12. Applying now this property of logarithm, 12 times the logarithm of 3. And this is what we will compute in our calculator, 12 times the logarithm of 3. You press in your calculator logarithm of 3. And the answer in your calculator, you multiply by 12. and you round off your answer to 2 decimal places, you should get 5.73. You can see that this is the greatest integer function of 12 times the logarithm of 3, and it's equal now to the greatest integer function of 5.73. 5.73 is equal to 12 times logarithm of 3, which we obtained from our calculator. And the floor of 5.73, or the greatest integer function of 5.73, is the biggest integer that is less than or equal to 5.73. And that integer, the greatest integer that is less than or equal to 5.73 is 5. The greatest integer function of 5.73, or the floor of 5.73, is 5 plus 1, we get 6, which is our answer earlier. There are 6 digits in the decimal representation of the positive integer 3 to the power 12. And we can find the number of digits in the decimal representation of a positive integer without writing all the digits, without actually writing the decimal representation of the positive integer. We take another example. We find the number of digits in the decimal representation of the positive integer 2 raised to 25. And we apply the greatest integer function. By using the greatest integer function, the number of digits in the decimal representation of the positive integer 2 raised to 25, denoted by n, is equal to the floor of the logarithm of a plus 1, where a is 2 to the power 25. And to the logarithm of 2 raised to 25, we apply one of the properties of logarithm. The logarithm of 2 raised to 25 is equal to 25 multiplied by logarithm of 2. And we take its floor and we add 1. And this is what we will compute in our calculator, 25 multiplied by logarithm of 2. And we round off the answer to 2 decimal places. We start with logarithm of 2. And the answer in your calculator, you multiply by 25. And you round off your answer to 2 decimal places and you should get 7.53. Now you find the greatest integer function of 7.53, or the floor of 7.53 is the greatest integer less than or equal to 7. And the greatest integer less than or equal to 7 is less than or equal to 7.53 is 7. Again, the floor of 7.53 is the largest integer that is less than or equal to 7.53. And that integer is 7. And to 7 we add 1. And 7 plus 1 is 8. Therefore, we conclude that the decimal representation of the positive integer 2 to the power 25 has 8 digits. We did not actually write the decimal representation of this positive integer 2 raised to 25, but now we know that its decimal representation has 8 digits. Now we check if 8 is correct by actually writing the decimal representation of 2 to the power 25. Using your calculator, you compute the value of 2 raised to 25. 2 to the power 25. And you should get 33,554,000. The decimal representation of 2, the positive integer in exponential form, 2 raised to 25 is 33,554,432. And counting the number of digits, we have 1, 2, 3, 4, 5, 6, 7, 8. And so our answer is correct. There are 8 digits in this decimal representation of the positive integer 2 raised to 25. For your practice, please try the following exercise. Find the number of digits and in the decimal representation of each positive integer given. Check whenever possible. Number 1, 7 to the power 21. 2, 3 to the power 89. 3, 14 to the power 7. 5 to the power 18. And 5, 9 to the power 78. For numbers 2 and 5, if you write the decimal representation of these two positive integers in numbers 2 and 5 using your calculator, the answer you will get there in your calculator is in exponential form. That is a decimal number multiplied by 10 to the power raised to some exponent. And so you will not be able to count exactly the number of digits in the decimal representation of these two positive integers if you will write their decimal representations using your calculator. So it's not possible to check the number of the digits in the decimal representation of these positive integers in numbers 2 and 5. But you can check your answers for numbers 1, 4, and 3 using your calculator. And that completes our lesson for today. And we will continue with decimal representation of positive integer in the next lesson. If you have questions about the lesson today, you ask your questions in the comments below. But don't forget to subscribe to my YouTube channel, Art Calison, the channel of learning and leisure. Thank you for joining me in my class today in number theory.